So in this lesson, we're going to continue our exploration of covalent bonding. We started out with a lesson that dealt with bonding in general and looked at sp3 hybridization and single bonding. Then we went to a lesson where we did double bonding, and now in this lesson we're going to look primarily at triple bonding. So let's turn our attention from single bonds and double bonds to triple bonds. Now there's been some research done that's found that there's I forget how many, but there's they found a way to actually do like 8, 9 some bonds or something. We're only going to triple bonds because in nature that's really all you have is the maximum of triple bonds. Okay. Nobody in here is doing welding? No? Okay. So in welding, actually you don't really use it in welding so much. You use it more in cutting steel. So there's a cutting torch, okay, that's used to cut steel pieces to get out if you need to, or cut holes in it or whatever. And that uses a gas called acetylene. All right, so acetylene has a triple bond. All right, and that's what provides all that energy. It's breaking up that triple bond that gives away all the energy that allows acetylene to do what it does. But there are lots of other things that have triple bonds in them. Let's see here. I shouldn't say a lot. There are a number that have more than one. Let's see. Why don't we do acetylene since I'm talking about it anyway. Now, in the next unit, we're going to learn to name these organic compounds. And acetylene is a common name for this chemical. But in the formal system that IUPAC, International Union of Pure and Applied Chemistry, is responsible for, the formal name for this would be ethine. Okay, so all we have are two. Eth means two carbons, and yne just means we have a triple bond. So if we have two carbons, we'd say this is C2, and I want to tell you in advance, how this works. I'm going to show you. We're going to have also two hydrogens. Okay, so remember that in order to make this work, we need to have how many total electrons around the carbon when we get finished? 8. How many are we starting with? 4. And how many electrons does the hydrogen need to be finished? 2. And how many does it start with? Just 1. Okay. So I want to put a hydrogen here with 1 electron dot representing the valence electron in the hydrogen. Actually, this is only electron. Carbon, while the carbon atom has 6 electrons, we're only looking at the valence electrons. So there's 2 electrons in a lower energy level. In the highest energy level, the valence level, there's only 4 electrons, so we can use 4 dots. And there are 2 carbons. And here's the other hydrogen. So what I want to do now is to show how these might share electrons in a way that gives the carbons, both carbons, 8 electrons, and the hydrogen, the 2 electrons at once. So let's start with the hydrogen because that's kind of the easiest one. We know it's only going to have 2. And the carbons, I know I can share 1 here. But the only way to get the 2 carbons up to 8 using this number of atoms is to bond not only this 2, but this 2 as well. Okay? And so that's how we get a triple bond. So we're going to then write the Lewis dot formula from this. So we started with electron dots. The black part of this is the electron dots. The circles represent where we're sharing electrons. So now that we've put the circles in there, we have a sharing arrangement. So we went from electron dot formulas to a sharing arrangement, and now we're going to do the Lewis dot formula. So we're going to squeeze the electrons between the atoms. So this hydrogen to carbon bond is going to look like that. The carbon to carbon bond is going to have 6 electrons in there. And the traditional way of doing that, the accepted way of doing that, is to do it like this. Okay? Got it? Like the buttons on a double-breasted suit. Okay? And then the last hydrogen goes there. Okay, so that's a Lewis dot formula for acetylene or ethine. And so we've got Single bonds in here. There. We've got a triple bond in here. And we've got a second single bond there. Okay? Remember, single bonds are always sigma bonds. For the triple bond, well, we've got to have all these bonds in different regions of space. Some way that we can have pairs of electrons grouped up in the same region, but keep those pairs separate. So I need 3 separate regions in which to put these electrons, but still have them sort of trapped between the 2 carbons here. Okay? So I'll just make sure we're clear on this is a single bond, going to be a single bond over here on the left side, and a single bond over here on the right side. All right, so let's take a look at what's going on between these 2 carbons first. So I'm going to write the carbon symbols here. These are the carbon nucleus or atom center, because really we're talking about the nucleus and the first layer of electrons that don't get involved in any bonding. We do have to have a sigma bond. So the first bond is going to be the sigma bond in between the 2 nuclei. All right. Sigma bonds and lone pairs are always going to come from hybridized orbitals. Okay? And we can only have, well, let's go ahead and put our hydrogens over here so we can be clear about this. And that's going to be a single bond, so that's a sigma bond here. Single bond and a single bond here. Okay. Let's take a look at what's going on with the, before we finish this out, let's take a look at what's going on with the carbon in the orbital notation for that. Okay, so here's our carbon, and we had a 1s sublevel. We have a second primary energy level, 2s sublevel, and then we've got a 2p sublevel. So the 1 tells us the primary energy level, S tells us the sublevel. Each of these boxes represent orbitals. And so this is 2p. Since carbon has 6 electrons, it has 6 protons, so a carbon atom has 6 electrons. We're going to have 2 more electrons. We put 1 in each box here. So that's the unhybridized set of orbitals using orbital notation to represent it for carbon. We only going to have, for each of these carbons, we're only going to have 2 hybridized orbitals. Remember, sigma bonds come from hybridized orbitals. Lone pairs come from hybridized orbitals, but we don't have any lone pairs in the carbon. So we're only going to have 2 sigma bonds. So we're only going to hybridize 2 orbitals. Okay? So we are only going to hybridize these 2 orbitals. Okay? We're going to hybridize these. And so these 2 over here on the end, we are not going to hybridize. Okay, not going to hybridize those 2 on the end. And so this follows the same sort of pattern I showed you yesterday, where we took and drew it out so that we had the hybrid set. Here's our carbon, and 1s doesn't change because it's a lower energy level. Those aren't involved in any bonding, so they don't need to change their shape. We're going to take these 2 orbitals here, one of the s orbitals, the first of the p orbitals. We're going to put them together and make a new set of hybrid orbitals. And these 2 p orbitals over here on the end, we're going to leave those alone. They're going to remain as p orbitals. So these are still 2 p orbitals. Okay? All right. When we hybridized all 4 orbitals in the valence level, we call that sp3. When we hybridized 3 of the orbitals, 1s and 2p's, we call it sp2. What do you think these are going to be called? Just sp. Now, you can say sp1, but you know, we don't usually put coefficients of 1 because it's just the same number, right? 10 to the first power is still a 10. So we're just going to call this sp. And it's in the second primary level, so I'll still keep the 2 there, just because those electrons are in the second primary level. Just like in all the other hybridizations, we take all the electrons and spread them out over all the orbitals. Okay? We don't put 2 in here and go back and pair up 2. We put 1, 2, 3, 4. You go through all of them, and then if you need extra, go back and pair them up. So we have 1, 2, 3, 4 valence electrons. So in this fashion, in this arrangement then, all 4 of these electrons are available to share and create bonds. So we're going to have 2 different pi bonds between these carbons to accommodate all those two bonds that were going to come from here. All right, so let's remember pi bonds come from p orbitals. So I've got really, let me do this way. I've got one p orbital kind of coming out here, and I want to make it a little bit fatter. I keep failing to do that, okay, because I want to show you what we're doing here. And then one p orbital is kind of going to be behind it. Okay, that makes sense. Okay, I did it kind of lightly there. Let's see. There we go. Can you see it now? And I'll make it a little darker for you. It's not showing up on the camera too well. There we go. You see that now? So the other side of this p orbital is in the back over here. The other side of this p orbital is over here. Okay? So we've also got the other part of this here. Well, again, I didn't make it quite fat enough to be clear. And then this one's in front down here. So back on this side, it's going to be in the back. Okay? That makes sense? All right. And the same thing happens on this carbon. Okay? So we've got a p orbital here, and then a p orbital that's in where the antinode's in the back here, but in the front here, and this side is going to be like that. Does that make sense? Everybody following? Yes, sir. All right. Remember, p orbitals reach out at 90 degrees to connect to each other, right? Yes or no? Yes, you remember that from yesterday? So this one, what we're trying to represent here on a two-dimensional sheet of paper, and it's kind of hard to understand unless you've done art and you understand what perspective means. These look like they're like straight up flat on the paper. But in fact, what we have are two different orbitals here. Let's see. We have an orbital that's more like this and an orbital that's more like this. Does that make sense? And the same over here. Okay, so I want you to imagine that that's what we have. Okay, I'm turning it sideways so you can see. They're basically 90 degrees to each other. We're tilting them in here like this to show, well, let's see, let's do it like that so you can kind of see what's happening, okay? See what's going on? All right, so I'm going to take this orbital and have it reach out and touch the one that is parallel to it over here. So this one here, where the front part of this node comes out toward you, is going to connect with this one that comes out toward you, and the back part's behind it, so it's going to connect in the back. Let's see here. What I need to do is to be careful about how I draw that so I don't cover them up. That's going to get a bit more complex. And let's see here. Orange. I'll use orange. So this one here is in the front here. So do it over here like this. But it's in the back here. Kind of hard to figure out what's going on, isn't it? Harder to see, isn't it? So I really should have kept this blue bar sort of a dotted line back there, so because it's kind of hidden back behind is what it should be. If that helps you to understand what's going on, I hope it does. And so we got a blue line that's going back here like this. All right. Talk about complex, huh? It's hard to see on a two-dimensional sheet of paper, isn't it? Okay. Well, let's see if we can label all these. And these are where the balloons are going to come in tomorrow. Okay? Because you're going to make models of all these different types of bonds, so that you can see what's going on. Remember, these are sigma bonds. Here, here, and here. These are all sigma bonds. Okay? But I've got two different pi bonds up here. Okay? So do you want to call the blue one pi x, y, or z? Nobody cares?
Z.
Z, she says. All right, so pi z is going to be this blue here, and pi z is going to be this blue one here. Okay? Which means the orange one then is going to be either X or Y. Which one do you want it to be?
Y.
Pi Y. So the orange one here is pi Y. So I'm going to put pi Y kind of on top of this. You can label any way you want to see what's going on. All right? Got it? Okay. Let's see. We've got 2 electrons here, correspond to these 2 electrons right here. We've got 2 electrons here, correspond to those 2 electrons in this Lewis dot formula here. We've got 3 pairs of electrons bonded between the 2 carbons. So there's 2 electrons in the single bond, 2 electrons in pi Y. I should have made one up and one down. Let me change that. And 2 electrons in pi Z. I don't know how to stick it in there. I'll have to put it over here somewhere in my drawing. Okay? And I kind of made this small so I could get all of this kind of on the screen at one time. Okay, I could have made it in a big picture, turn the paper sideways. It'd be easier to draw that way, wouldn't it? You'd be able to see what's going on a little bit better. But do you understand what we're doing? Mm-hmm. Okay? So that's a triple bond. All right? Does that make sense to everybody? All right, and here's our hybridization for it. Okay? So what we have here is we started with electron dot formulas, or electron dot notation rather, and we did the sharing arrangement. We went to, from there, creating a Lewis dot formula, and then we figured out what the shape of all the bonds were going to be. At the same time, we're also figuring out what the hybridization is going to look like. Got that? All right. So I'm going to turn you guys loose in your small groups now to work on another one where there's a triple bond. Okay, I'm telling you up front there's a triple bond. Later in this unit, you'll have to kind of figure out whether there's a triple bond or double bond or single bonds. Okay. So the most abundant gas in the atmosphere is nitrogen. Nitrogen is one of the diatomic elemental gases. All right. You need to know that nitrogen, oxygen, fluorine, chlorine, and hydrogen are all diatomic elemental gases in their natural state. That means that hydrogen is not just H in the atmosphere, it's H sub 2. Oxygen is not just O as it exists in the atmosphere, at least most forms of oxygen in the atmosphere are not just O, it's O sub 2. Fluorine, if there's any in the atmosphere, we hope not because it's pretty poisonous, it would be F2. Chlorine, same thing, it's pretty poisonous. In fact, there was a city in South Carolina I don't know, maybe a 10 to a dozen years ago now, they had a train car derail in the middle of the night filled with high chlorine gas. A lot of people, some people died, and people have permanent lung injuries because of this chlorine gas. So if you ever see yellow gas floating along, get away, okay? But anyway, this is Cl2, okay? So nitrogen then is N2. Of course, it's pretty innocuous. It's a very stable gas. It won't hurt you. You know, every time you breathe in, about 70% of what you're breathing in is nitrogen. Okay, and that's a good thing. If our oxygen contents were way higher, it'd be bad for us. Okay, we get something called oxygen narcosis or something. I think is what it's called. Okay, don't hold me to that term. I don't really remember. Okay, but it's not good. We're basically designed. Our bodies are designed for 70% nitrogen and about 20% oxygen, 21% oxygen, and 23, 24. It's not so bad, but 50%, 70% oxygen, not necessarily a good thing. It really depends. They used to put high content oxygen in the Apollo moon rocket, the capsule that put men on the moon. But then they had a fire in one of the capsules. All the astronauts died. They stopped doing that. So, not a good thing. Okay, you don't want too much oxygen. It's too easy to burn things, and we don't want that. So anyway, back to this. So I'm going to have you do this same stuff. Okay, electron dot formulas to sharing arrangement to Lewis dot formula, the shape of all the bonds, and show me how this hybridization occurs using orbital notation for N sub 2, nitrogen as it appears in the atmosphere, natural atmospheric nitrogen. Okay. So nitrogen is N2. Here's our sharing arrangement, electron dot formula, and the shape of all the bonds. Okay, I made it a little bit bigger. Hopefully it's a little easier to see what's going on this time. Now, nitrogen is right next to carbon on the periodic table. So it has one more electron than the carbon does. So here we have 1s, 2s, and 2p orbitals. But now nitrogen has 7 electrons total, 2 in a lower energy level, and 5 in the valence level. So 1, 2, 3, 4. Actually, I should have put 2 in here and then went over there. Okay? Because you always pair them up in the S sublevel, then go to the next one, right? So let's go to the form of the hybridized orbitals. Actually, I label this 2p. Remember, what we're going to do is, if we're going to have 2p orbitals, or 2 pi bonds, we need 2p orbitals on each nitrogen. Okay? So these 2p orbitals are not going to be hybridized. This S and P do become hybridized because I need a hybridized orbital for my lone pair over here and over here. So each nitrogen has one lone pair, and I also need a hybridized orbital for the sigma bond. Okay? And so we're going to leave the 1s the same way it is because it's not involved in bonding, it's not involved in hybridization. And so we're going to take this 2s here and this 2p here and make that into a new kind of orbital called sp. It's in the second primary level. And take these two orbitals and make them into, or keep them as p orbitals in the second primary level. Okay? And so we got 1, 2, 3, 4, 5 electrons. We're going to put 1, 2, 3, 4, and then put the 5th in here, pairing it up there. So when we hybridize orbitals, we're going to share the electrons, or put the electrons in there as if they're all the same set of orbitals, okay? Not like they're separate orbitals, all right? And so up here, I would have put 2 electrons here, then put 1 each here, and then if I needed to, go back and pair up. But when we hybridize, we put the electrons in all 4, regardless of whether they're the same or a little bit different in the hybridized and unhybridized set in that energy level. Okay? All right. This then gives us 2 electrons in a p orbital to make this pi bond and this pi bond. And then we've got 2 electrons in this orbital for this lone pair over here, correspond to the lone pair up here in our Lewis dot formula. Okay? And then we've got 1 electron in a hybridized orbital available for a sigma bond to share with another nitrogen. So this nitrogen has an electron to share with this nitrogen, and so in the bond we now have 2 electrons, and this is a sigma bond. Okay, and then these two orange orbitals up here are orange. They become bonds once they share the orbitals. This is pi. Do we want to call it pi x, or pi y, or pi z?
Pi X.
Pi x, she says. She's the only one speaking up. I mean, if you guys want a different one, you got to say so. Somebody else, pi z or pi y for the pink one? Pi y, she says. Okay. Pi y and pi y. Okay. Got it? And so, and we've got 2 electrons in this orange orbital, better do that up and down, and 2 electrons in the pink one as well. Okay? Remember, the 2 pink parts are part of the same orbital, not different orbitals, same orbital. Pi bonds have 2 parts, okay? Pi bonds have 2 parts. Please remember that. Any questions about all of this? You're all good? All right. So let's start looking at how these hybridizations work then. So if you will get out a set of 4 balloons, all of different colors, and blow all 4 of them up and tie knots in the end of all 4 of them, and then I'll show you how to put them together. So you should have blown up two balloons of two different colors. Okay. So let's say, and then you're going to tie those off, and you're going to tie them together, so you get something that looks like this. Okay, when you tie them together, right?
Yes.
Yours may not be pink and orange, but you get the idea, I hope. And then you're going to have another set of two balloons that you're going to blow up and tie a knot in and tie them together, so you get another one of these. Okay? Then all you have to do is push those together, okay? And you have a set of what hybrid orbitals look like. Okay?
I like it.
And so when you push them together, you get something that looks like this. Okay? So this is a set that represents sp3 hybrid orbitals. Okay? Now you need to label them as such. Each one of these are going to be labeled as an sp3 hybrid orbital. Okay? On all four of them. You're going to write it on all four of them, yes. Okay? In your notes, we want to have a drawing of this, okay? But I want you to have a drawing that takes you from the unhybridized orbital to this hybridized set, okay? So the unhybridized orbitals, remember, had double balloon shapes, okay? So we had an s orbital that's roughly spherical. Okay, there's a nucleus in the center. All these have the nucleus in the center. And so we had a set of orbitals. The p orbitals would have, this is s, the p orbitals would have been double balloon shapes. Okay, so this would be our S and P orbital. So this is S. We'll call this at PX. Not that it matters which one is PX or PY or PZ. PY here maybe, and PZ here. Okay. And then when you draw your set of hybridized orbitals, let's make sure we show how we got from here to here. Okay, so this green set of orbitals with two antinodes become this green one back here in the back. So this is representing this hybridization process. This orange one here represents a hybridization process. Let's see now. I got to do the pink one still. So the pink one represents a hybridization process.
Yeah. Just a little more from here.
And the blue one's change from S to the hybrid orbital represents a hybridization process. So don't try to make these drawings too small on your notes, because then it's going to be all jumbled up. It's hard enough to understand what's going on anyway from the drawings, but if you make them too small, then it really is going to be hard to tell what's going on. So this is what you have a new model for, okay? And you have, if you kept your model from the previous set, then you're going to have a model of what's inside the S. Not the S part, because we don't have a way of making a big round balloon or beach ball to fit them all in, but that's what you just kind of have to imagine the S orbital there, okay? Okay, in the class activity today with balloons, we're going to make models of this SP3 hybrid. We're also going to make models of an SP2 and an SP hybrid set of orbitals with the p orbitals that go along with those. So what I do is to assign work groups, and one work group of 2 or 3 students will make an SP. The next group will make an SP2, and then you just keep going around the room like that. So every other group is making an SP, every other group alternating from that is making SP2 hybrid orbitals with the p orbitals that go along with that. So an SP2 set of hybrids will have a p orbital that's not hybridized. Okay, so that's a double balloon shape, and the nucleus is going to fit right here. In addition to that, then the S, this is, let me label this as being SP2. Okay, then an SP2 has 3 hybridized orbitals, so those are single balloon shapes. Let's make those. Here's a pink one, and a green one, and an orange one. Okay, so you can put those 3 together, and then you're going to take this set of p orbitals, so these are p's, and this either has to be labeled px, and both these are part of px. In a p orbital, you've got 2 nodes or 2 antinodes, so this is either, both of these are either both px or both py or both pz, and it doesn't matter to me which one you label that. And these are just simply SP2 hybrids. You would label those as SP2 hybridized orbitals. All 3 balloons are labeled SP2 hybridized orbitals. This set of balloons gets turned from here to 90 degrees to that and just stuck in there. Okay, so that's the way you make an SP2 hybrid set of orbitals, SP2 hybrid set of orbitals with the p orbital that fits in there. So the p orbital is basically 90 degrees to all of this. You just turn it up 90 degrees and stick it right in there. And you tie 2 of these together and tie the 3rd one in the middle there to get that set of 3. So, as I said, half the class has a group that together is going to make a set of SP2 hybrid orbitals with the p orbital that sticks in there and build that model. When they're done, they need to draw that in their notes, but I'll get back to that in a moment. Then for an SP set of hybrid, you need 2 p orbitals. Okay, so you've got, well, we can go ahead and make it blue like that. You've got a p orbital that's not hybridized like this, and you've got another p orbital that's not going to be hybridized. And then you've got a hybridized, 2 hybridized orbitals, okay, and those are going to be made up and then tied together. So these are your 2 hybridized orbitals, and they will be labeled hybridized orbitals. These are p orbitals. They'd be labeled p orbitals. This one might be px, but if this one is px, this has to be py. If this is pz, that has to be, can be py. So basically they're on 2 different axes, so they can be either px If that's px, this is py or pz. If this is py, this is either px or pz. So you just have to have them on the x, y, or z axis separately. Okay, we've done unhybridized orbitals, and you should know how to do the px, py, pz thing. So this is a set of sp hybridized orbitals. So this will be labeled sp hybridized orbital. This is labeled sp hybridized orbital. And they're going to be put together in exactly the same way as our original p orbitals. This set is put together with this set, and the third set just kind of stuck in the middle of it to make the whole sp hybridized orbitals with the p orbitals that go along with those. So those models have to be done in class. Okay, so every alternating work group makes one of these or one of these. Okay, so this group makes, the first group would make this, the second group would make this, third group makes this, fourth group this, and so forth. Now, the homework is whichever of these models you made in class, you have to make the other one individually at home. So if you made an SP2 set of hybrids in class, then at home you need to make a set of SP hybrids with the p orbitals to go along with it. Okay? So that's the idea. I want you to do the balloons at home. Now, before you're done, you need to have illustrations in your notes. It's not enough just to make balloons. Balloons are fun and all that, but it doesn't help you at all with the content unless you understand what these models are telling you about the shape of orbitals and the way it's all going to go together into molecules. So here is the shape, the drawing I showed you earlier, where we showed how this p orbital becomes a hybridized sp3 orbital back here. This green set of two balloons becomes one balloon over here. And the two orange balloons becomes one sp3 hybrid here. And the blue s orbital here, the spherical orbital, becomes one hybridized orbital here. Okay? You're similarly going to do the same thing with this model when you're done. So you'll have a set of 4 orbitals. Okay? You'll have a p orbital that's going to be going up and down. You're going to have these around the center. So let's see if I can help you out with that a little bit. So let's say we did it like this. Here's this hybridized orbital here. And then I'm going to turn this so the green orbital is sticking out toward me. And then the orange one will be back kind of behind things. And then the p orbital here is going to be vertical in this whole system. All right, so when you get it all together, that's what it's going to look like. And you want to have a drawing that starts with this set of unhybridized orbitals showing how those become all these. So really I should have color coded this a little bit differently because the S never becomes a p orbital. Okay, so let's say, just for the sake of argument here, that our S became this pink one. Okay, so you're going to draw an arrow from this S to this pink to show that's what the hybridization is. Okay, the S became this pink one. Then say this p orbital here, this green one, became this set of blue ones. So when you do it, if you're color coding these, this should be green here and this should be blue over here, okay, instead of the colors that I did this with. So the idea is this p orbital doesn't change. It's two antinodes with its p orbital here. This is the same p orbital here. All right, if you choose it to be px, it's px. If it's py, it's py here. So the p orbital doesn't change, but all these other orbitals hybridize into these single balloon shapes. All right, so this sp set of hybrids then are going to work pretty much like our unhybridized set of p orbitals here. They're going to look kind of the same. So let's see. Let's put our two hybridized orbitals like this, here and here. So I'll put the green hybridized orbital sticking out to this side. Let's see how's that going to go with my original. I want to make it. I want to make our S. I got my color coding a little off here again, but so I'm gonna have to keep going with this system here. So the green hybridized orbital is going to be over here. The pink hybridized orbital is going to be coming over on this side. Then let's take this one and put it right here vertically. And then the blue one's going to be coming out toward us and back away from the paper. And so this dotted part here really doesn't need to be dotted because it's not hidden behind things, okay? So this is a set of sp hybrids with the p orbitals that are unhybridized. So the two orange antinodes here are a p orbital, either px, py, or pz. And the blue set here in this organization, this arrangement, this blue set here is going to be, if this is px, this has to be either py or pz. Doesn't matter which one, as long as your axes are different. Okay, so these are two. The pink one here is an sp hybrid orbital. The green one is an sp hybrid orbital. And what you want again is an illustration that starts with, in your notes, starts with this. Okay, so basically all of this stuff over here is just showing you how to make your models. You don't need these in your notes at all. You need these two in your notes. But adjacent to these, you also need the unhybridized set here and here with arrows showing how each of these parts become one of these hybridized or unhybridized orbitals. Remember that the s orbital always becomes a hybridized orbital over here. Okay, so my s might be either this, draw an arrow from this s to either this pink or this green. Okay, the p, one of the two p orbitals or one of the three p orbitals becomes the pink or green, the opposite of whichever one. One's s and one's a p orbital became a hybridized orbital. But you're also going to have p orbitals that didn't change. So this p orbital might become px, might become this px, and this pz here might become this pz here. All right. So the idea is to show that the p orbitals, two p orbitals, are not going to hybridize, and the s and one of the p's hybridizes into this and this. And up here, p orbital doesn't change. One of the p orbitals doesn't change, and the s and two p's become these hybridized orbitals here. That's what I want you to get out of this whole activity. So if you did this set, SP2, in class as a group, then at home you are individually going to be doing an SP set. If you did an SP set in class at school, then at home for homework you're going to be doing this set.